Okay, the purpose of this video is to walk you through this quick start for beginners of TensorFlow. TensorFlow is Google's platform for machine learning, including neural networks. Keras is the specific part of TensorFlow that deals with neural networks. Now, just to get you on this page, you can see the address here, tensorflow.org/tutorials/quickstart/beginner. Now, you may feel that we're starting sort of in the middle somewhere, and you don't understand everything that's going on. But just bear with the flow and try to understand what you can. And you can also Google some background concepts if you're missing something. But this is like a new language, and a good way to learn language is by immersion. So I'll try to explain some things that you may not understand and other things you can look up through Google. Now, the very nice thing about this setup is that you can actually run the code. There are two ways to run the code. One is to run in your browser on Google Colab. Another way is to download the notebook and run it in Anaconda on your own computer. So starting out, we'll run in Google Colab. Maybe later on, we'll download the notebook and you can run on Anaconda. But this is very easy. You just run in Google Colab here, and then this sheet becomes live. You can execute the code in the sheet and see what's going on with it. All right, so let me go ahead and close this off for now. And in this particular quick start, we're going to build a neural network. Now, I posted some videos that give background on what neural network is. Basically, neural network consists of layers. The input to the first layer is your raw data, and the output is some kind of classification. Now, in this case, we're going to build a neural network that classifies images. Now, when you start out building the neural network, there's no way it can tell what the images mean. So you have to train a neural network, and this involves a training set that you use to tell that the neural network learns by trial and error, and then finally evaluate the accuracy of the model. I think I mentioned in the previous video that this is kind of system is actually used in practice to do digit identification. And this was one of the great early successes of neural networks. All right. So let's see. So here it says this is a Google Colaboratory notebook file. Python programs are run directly in the browser, so that's what's going to happen here. All right. So here it says in Colab, connect to a Python runtime. At the top right of the menu bar, select Connect. Let's see what it says here. Now we are now connected. Okay. I don't know what the additional connection options are, but I think we're fine. This would be fine. All right. So let's see. So it says upgrade tip to install the TensorFlow2 package. So let's go here and do that. Here I can run this cell. And it has been executed. So as I said, TensorFlow is the package that creates the functions that we need. Now what we're going to do is take a bunch of images of digits and classify them. And those images are in this data set. Now you can take a look at this link. I'll open it in another tab. This is just about the data set. You can look at this if you want or not. So this is just some background. This guy, Jan LeCun, is one of the pioneers of this field, and here you can see the number of images. A lot of images. Here we have 9 megabytes of training images, and let's see how many there are. So 20 by 20 pixels. So here we have 30,000 patterns. So this is a large data set. You need to use neural networks with large data. So you notice that you have training and testing. All right, so they're both there. The training set is typically larger than the testing set because usually, of course, training is like doing homework, and then testing is like doing the test. So usually you do more homework than tests. So Same thing with machine learning. So let's go back here and do that. Okay. So here we have to load this data set. And this is already contained in this Keras, which is the sub-library of TensorFlow that creates neural networks. So let's go ahead and load this. And it's downloading the data. There we are. It may take a little while. Oh, it's done. It's already done. Wow, that was fast. All right. Now, what do we have here? Xtrain, Xtest. Here you're dividing by 255. Now, why do you divide by 255? Well, you need to know that when you have an image, the image consists of pixels, and each pixel has a numerical value. I can demonstrate this, and you can see yourself using the Paint. You have Paint is one of your programs in Windows. It's not going over. Let me move it over. I don't know why it's not going over. But I'm going to open up Paint. You can open up Paint by clicking on the magnifying glass and typing in Paint. So here's Paint here. All right. So let me make this a little bit bigger. And let me go ahead and make a dot or something. Here we go. Let's try this. So we got this, and let me go ahead and fill it. If you've ever done this, I think. All right, there we go. We got a fill dot. Now let's zoom in and see what it looks like. Okay, now when you zoom in, of course, you can see it becomes more and more jagged. I don't know how far it's going to let me zoom in. But you can see, as I said, it's becoming more and more jagged. And the reason it's jagged is that this image actually consists of black and white squares. In fact, you could change one of the squares. If I took this here, and I changed the color, maybe change this into gray, you go and click here. It will change one part to gray. Now, that's a square. And that's 1 pixel. All right, so let's go ahead and see what's going on here. I'm going to look at my medicine dropper, which tells me what the colors are. Where's my medicine dropper? Right there. All right, now if I do color picker, let's see what this says. All right, well, first I need to open my edit colors here. Now if you look at this, here you see some numbers here. Red, green, blue, 195, 195, 195. All right, so if I go all the way up, notice that it goes up to 255. So these are indicating the levels of each color, right? All right, so that's what's going on here. And as I go down, you can see that the number is getting smaller and smaller down to 0. So the number from 0 to 255 indicates the level of whiteness. 255 is white, and 0 is black. Now notice the red, green, and blue are all the same. That's what you would have in black and white. Black and white, red, green, and blue are all the same. So in our case, we do have black and white images. So every pixel in this image has a number from 0 to 255. Now we want to scale it down to 0 to 1 because then it's kind of convenient. You can also see that, so here you can see gray is going to be somewhere in the middle. All right, so that's what we have here. We have images that consist of pixels, and our images are quite small, only 20 by 20 pixels. You can see that there are lots of pixels in this image. 20 by 20 would be much smaller. See, this is quite big, 560 times 329. That's a much bigger image. So these are small images, and you can see that even with these small images, we need quite an elaborate training and testing set, as well as a fairly elaborate neural network. Okay. All right. Now, it would be nice to look at these here and see what they look like. Now, in order to take a look at some of these variables here, we have to know something about Python. But actually, if you look at this, it's really helping me. If I put my mouse over here, here it says that Xtrain is an ND array with shapes 60,000, 28, 28. What does that mean? That means, in fact, there are 60,000 images of 28 by 28 pixels. All right, so we've got 60,000 images to train on, and each one is 28 by 28 pixels. Why train? Well, what is why train? Well, we'll take a look in a moment. All right, so that has shape 60,000 also. Then we have X test 10,000 and Y test 10,000. So this is data that is from MNIST. So this was in the computer already. And as I said, we divide by 255. Now let's take a look at some of this. If I want to look at this, I can use, if I wanted to look at some of the data, I would use the print function. So for instance, if I want to print, all right, let's look at xtrain. Now, as I said, xtrain is a set of 60,000 images, each of size 28 by 28. All right, so let's do the first image. Now, one thing you need to understand about Python is that the first image will have index 0. So this square brackets indicates that I'm going to give images. Like you put a matrix in square brackets. Here I'm putting the matrix indices in square brackets. So here I want to do the image 0, and I want to show all 28 by 28 pixels. If I want to show everything, I indicate that with a colon. That's a shortcut to Python saying I want everything possible. All right, and then you put another colon here. Now let's take a look and see what this does. If I want to execute this, I can hold down the control and press enter, and you see it executing. All right, now see what you get here is a bunch of numbers. It's a little bit hard to interpret here. If we look at how this is arranged, here you see occasionally you see a square bracket. What you're actually having is 28 rows of 28 numbers apiece. All right, but this is quite difficult to interpret. So instead of showing the numbers like this, let's try to show the image. So I think this is not so easy to see. Let's see what ytrain is. Now ytrain only has one index, which is the index of the image. So let's look at ytrain of 0. So this would be the ytrain corresponding to image 0. And what we get 5. So what that means is that the label of this first image in xtrain is 5. Ytrain is the identifier. Now let's see if that matches up with what we would think. All right. So what we want to do is we want to plot the image, the graphical data for xtrain. And we can do that in Python using pyplot. So we're going to have to use this import a matplotlib. All right. Now see here it shows it for me because I typed this before. What that means is I'm going to take all the functions in this library and I call them PLT. All right. So in order to plot the 0 image, I'm going to do PLT dot, and there's a function called imshow, which is basically show the image. So it converts the numbers that you saw into an image. And I want to plot imshow xtrain. This is very annoying. I wish I could get rid of that. There we go. Plot imshow xtrain. And I want the 0 image. And I want to show all, I'm not sure why it's doing that. I want to show all pixels in the 0 image. All right, so let's see. Let's see what that looks like, and let's see if that corresponds to 5 like we would expect. Let's take a look. There we go. All right, now in fact that's a 5. All right. Okay, so I showed you some basic commands. Print will show you what's contained in a array. I showed you that these arrays have indices and how to access these arrays and how to specify them using indices. Remember, the colon means you use all the indices. So I have a little exercise here. So here again we have the training set and the testing set. Okay, so here's your first exercise. Number 1. Let's make this a little bigger. Find the first 9, let's make this a lot bigger. Find the first 9 in the testing set and give a screenshot of the corresponding image. All right, so each of the entries in the testing set should similarly have an image and a number associated with it. All right, so that's your first assignment. I will distribute that page to you. Okay, let's go ahead and move on. All right, now here we have layers. I don't know if you saw the movie Shrek. It says ogres have layers. Now, neural networks also have layers. And they're kind of key to the structure. And I explained in my video what the layers do. Each layer has a non-linearity. So when you add layers upon layers, you're adding complication to your function, which adds to the modeling capability of your model. All right. So let's look at what we have here. Model. All right. So this is my neural network model. tf.keras.models. Remember, Keras is the neural network component of TensorFlow. This is going to be a sequential model. Okay. So you have a linear stack of layers, one after the other. So I showed a picture of this in my talk. Maybe I'll go there and remind you of that. Well, I didn't actually show multiple layers in my talk, but here you can see 2 layers. Here's the input layer, and here's the first hidden layer. Now, if you add layers upon layers, you can add another layer after this, and so on. So that's what layers mean. Each layer consists of neurons, and the neurons have inputs and outputs. And as I said, each neuron has a nonlinearity. All right, so let's go back. All right. So here we have a couple of layers. You can see that there's the flatten, and then there's dense, and then there's dropout, and then there's dense. So what do these mean? So by the way, if you want more information about these different functions, you just click on the name here, and it will tell you what's going on. They really have designed this very well. So here's a sequential group of a linear stack of layers into a model, right? Okay, so this is specifying a sequence of layers. All right, now first you have flatten. No, I don't want to show that. Flatten, dense, dropout, and dense. So I made some notes here that I can make available about what's going on. All right, so again, flatten, dense, dropout, and dense. So flatten, what does that mean? Well, the input was 28 by 28, which is a table or an array. And we want to put these all in a single line. Now, there are some cases where you don't want to put data in a line because what you're doing is you're separating pixels that are close. For instance, this pixel here and the pixel right below it are very close. Now, you'd like to use that information in your neural network, but when you flatten, that information is lost. Later on, we'll see that in many image processing applications, you don't flatten. Instead, you use something called a convolutional neural network that preserves the adjacency of pixels that are next to each other. All right, so 28 by 28, that's 784 pixels. We flattened it. So we have 784 inputs. And then here it says dense 128. Now, that's not 784. So what happened? Well, you've got a 784, and these 784 inputs are connected to 128 outputs. All right, so we've got these connections here, and it's a dense, which means it's fully connected. Every input is connected to every output. Now that's a lot of connections. 784 times 128 is the number of connections. That's a lot of connections. But computers can handle that. The activation is the ReLU. This is a non-linearity in this layer, and I've talked about this in a different video. All right? So that's what we have. This is the number of connections. So my weight matrix has this size. And it says each weight matrix will have a ReLU function, which means that when the input goes in, when the total input goes in, I'll only take the positive part. If it's negative, I send it to 0. I only take the part that's positive. Here's the mathematical expression for ReLU. All right. All right. Now, there's one more here. I'm going to skip over this dropout for a second. Then we have another layer that's dense. So we get this repeated process. We get the 128 that goes into a 10 outputs. And here's a sample output. We get positive and negative numbers. All right. Now, what about the dropout? Well, what happens is you want to introduce some robustness into the model. You don't want to have it depend too much on any particular connection. So what you do is you make the connections fail at a certain probabilistic rate. Every time you train, and this is only during the training process, every time you train, you remove 20% of the connections. And that's what this 0.2 means. So you're removing 20% of the connections. And then you're only training on the rest. I mean, this is kind of like, well, for human beings, you're not paying full attention at any one time. So you don't want to use 100% of your brain to do any task. You want to make it so that it can rely only on part. And as I said, that makes it so it doesn't rely too much on any one particular connection. It also avoids connections working against each other. There's a lot of theory about dropout, but that's the basic idea. All right. So if you get the overall idea here, you have 784 inputs, which are fully connected to 128 hidden neurons. And these hidden neurons are connected to 10 outputs. Now, why 10 outputs? Because they're 10 different digits. Now, these 10 outputs will have positive and negative values. Now, remember, the ReLU only gave me positive, but remember, after I do the ReLU, I have another layer where I'm doing my multiply and add. I should say also here, I think I neglected to say this. So the variables, the unknowns in this model are the weights between these two layers. There's also something called a bias, which shifts this curve. Now, the weight can be negative, so that's why these outputs can be negative. All right? So that's why we get positive and negative outputs. Now, in this case, we don't use ReLU, so we can have positive and negative outputs. Now, what we want to do is decide which of these 10 classes is the most probable class. Okay, so my outputs are positive or negative numbers. Now, what I would like to do is instead of outputting positive and negative numbers, I would like to output 10 probabilities, where the probability is the probability that that particular digit is the right answer. Now, typically, in the real world, you don't get a yes or no answer. You get a probably or nearly or something like that. So the way to express that mathematically is with a probability. For instance, if I have a probability that's 4 of 0.7, that's a pretty high probability that 4 is the digit. But there might also be a non-zero probability that that's a 1. All right. So what I need to do is I have these 10 real numbers, and I want to associate these 10 numbers with 10 probabilities. And the probabilities have to add up to 1. And now probabilities are between 0 and 1. And actually they add up to 1. So the way to associate these numbers with probabilities is map positive and negative numbers to the positive numbers and then normalize. Normalize means to normalize so that they sum to 1. They need to sum to 1. All right. We'll see how that's done shortly in the code. Let's go back. I think I got a little ahead of myself. Oh no, I think I'm here. All right, we're good. So let me go ahead and execute this. Make sure it's executed. All right, that's been executed. So my model is loaded. And here's one example of the of predictions. This, I could put predictions here. I could say print predictions. Now what this is doing is this is just it's just finding the that it's just finding the output for the model for the first for the first training image. So let's see what happened. Okay. All right. So this is the output for the first training image. :1 means up to image 1. Remember, the first image is 0, so :1 means up to image 1. All right. This .numpy, we can ignore that for now. But this is the output of the model. All right. So here we have numbers from 0, real numbers, and we want to convert these to probabilities. And let's look at how this is done. If I look at softmax, look at what softmax does. It takes the exponential function. It takes the exponent, and now you should know that the exponential of a positive or negative number is a positive number. And then here you take the sum of all the values. All right. So if I take a bunch of negative numbers, let's do an example to show what's going on here. Okay, so let's do a simple example. Get my draw here and get some, okay. Okay, let's say my outputs are, let me make it easy for myself. Let's say -1, -7, whoops, -7, 3, 2, okay, -4, 8. I don't need to give all these numbers. Let's say the last one is 9. Okay. All right, so I have positive and negative numbers. So I want to convert to positive. So that's going to be the exponent of -1, whatever that is, e to the -1, e to the -7. Now, e to the -7 is very small. E to the 3, e to the 2, ... up to e to the 9. Now these numbers, e to the 9 is also very big. So these numbers obviously do not add up to 1. So then if I want to normalize, means I'll take these numbers and divide by the sum. So that would be 1 over e to the -1. Sorry, that's a plus. E to the -1 plus e to the -7 plus ... up to e to the 9 times these numbers. E to the -7. Okay. Now when I write this number out here, I mean I multiply this number into each one of these components, just like you do with a vector. So it should be a straightforward exercise to show that the sum of the resulting 10 numbers is going to be 1. So that means that I can interpret them as probabilities. All right? So that's helpful. All right? And then that's a way of converting my inputs into probabilities. And you can see here that these are the numbers here. I can verify that this sums to 1. The way I do that is I can set this equal to a variable. I'll call it check. I'll call it probs. All right, now I want to find the sum of the values in probs. Turns out to do that, I need to import NumPy, which gives the numerical functions in Python. So I'm going to import NumPy as NP, and then I'm going to print, then I'm going to print, I don't know why it always does that, print, then it's going to be np.sum, so that's the sum function from NumPy of probs. Okay, and we'll see what happens here. 1.0. So in fact, the sum of those numbers was 1. Okay. All right. So that's what we're going to have here. All right, well, I'll stop here with this model. This is setting up the model. The next part will be about training the model. All right?